many editors and all such things. We'll just see here in more in detail, like what are the different applications of compiler technology. Okay. Yeah, moving on. The first thing is whenever you are trying to implement high-level programming languages, you need a compiler, because high-level programming language is like, for a programmer it is easy for to write. Okay, but then for the machine it would be difficult to understand. Okay, because it you already know it only understands machine language. Okay, the first thing is, so the first application is like, depending on the high-level programming language, how it has been implemented, the compiler technology has to be developed. So as I mentioned, I mean, as you already know, what are the different features are available for high-level programming language. Okay, so every high-level programming language has this common feature, that is abstraction. And then what is abstraction is like, you are just trying to express what the task has to be done through the algorithm, or it could be a flowchart also, and understand that algorithm and flowchart and try to write the code. Okay, and after doing, what does compiler has to do? It has to translate the program into target language. Now, what is the target language? It is the machine code. Okay, so that's how till now we have been using a compiler for translation. Okay, so I've already mentioned it is always easy to write the program in high-level language because there are many features and it's readable. You can make out error to find the errors, I mean debug the program, or you can it is easy to modify also. So everything whatever it's required for a programmer to make programming more readable and more efficient, high-level programming language will help us to do. Now, when it comes to uh, a compiler, okay, so when it has to translate, so there it can become a less efficient. I'm talking about the compiler here. So when it is less efficient, the target program, the machine code, maybe it will run very slowly. Again, you know, we know there are lots of high-level programming language, and compiler has to make sure that it supports all the languages. Okay, so next thing is like writing low-level language. Maybe it has more control over computation, more computation in the sense to get the target values. Okay, maybe it is comfortable to get target values directly, but then it is more it cannot give us the um, easy way of writing the code, but then it can produce efficient code also. But we know low level programs, when we take up to write, it is less portable, it can be prone to different errors, and obviously it is harder to maintain in the sense uh, to modify, I mean to update the program as and when new features have been added. That is called as maintain of programming programs, right? Okay. Now, moving on with the same high-level language, there are like lot of programming language which has aggregate data types. Aggregate data types in the sense they are supporting arrays, structures, many high-level control flows such as loops and procedures, and all of these concepts are familiar to you. Okay, so when all these high-level constructs or data access operation try to translate directly to a machine code, uh, yeah, the result would be very inefficient. So always, whenever these kind of loops or data structures or arrays have been used, okay, there comes the data flow optimization. Okay, to what does it do? It analyzes the flow of the data through the program and try to remove all the redundancies across the constructs. So we can get the effective code whenever this kind of aggregate data types were used. Next, it's about all programming languages have these kind of aggregate data types used, but then if we come up with, if we talk about the feature called object orientation, so that's been used in some of the programming language like Smalltalk, C++, C#, Java, right? So there are a lot of, other than these two, there are a lot of other features, right? Maybe data abstraction, inheritance of properties, polymorphism. Okay, so there are many uh, features. Okay, and as a compiler for that particular object-oriented language, it has to take care a lot. Okay, coming to particularly Java language. Actually, a Java language is type safe, and you know that well. In that case, object cannot be used as an object of an unrelated type. All array accesses are checked to ensure that they lie within the bounds of the array. That is a main feature of Java language. So compared with other programming language here, Java has no pointers and does not allow pointer arithmetic. It has built-in garbage collection facility so that automatically frees the memory. Compiler optimization have been developed to reduce the overhead. Now, next is the Java is designed to support portable and mobile code. Programs are distributed as Java bytecode, which must either be interpreted or compiled into native code dynamically, that is at runtime. So, dynamic compilation in the sense, information can be extracted dynamically at runtime, and it can be used in a better optimized code to get the better optimized code in the sense. So this is about generally they have talked about few programming language and features. Okay, so all these features, whenever we are trying to implement compiler, so we should take care of all these features. That's it. Moving on. Now, whenever we are trying to build a compiler, it's not about only a programming language we use to write programs. Okay, it is about the computer architecture also. Okay, where the programs has been the softwares have been installed, and for that software, you are trying to install whether code blocks or whether Eclipse or anything into a computer, right? So however the architecture is as a computer, for that thing also it has to be supportive for the compiler whichever I've developed. Okay, so there are two features which are mainly concerned about the computer architecture here. Okay, one is parallelism and memory hierarchies. There is always a rapid evolution of computer architecture. It's not like computer architecture is it's just a static that can be used. Okay, so even now there is an evolution of computer architecture, and as the computer architecture evolved, so there are and for a new compiler technology. Now, parallelism, coming to this particular definition. Okay, so it can be found at several levels, in the sense at the maybe at the instruction level where multiple operations are executed simultaneously, or it can be seen at the process level where different threads of the same application run on different processes. Okay. In general, I can say there are like many programs which will be run at parallel. Okay, so that's a concept here. And now to support this parallelism, how the compiler has to think of, and that is the main thing which we have to take care now. Next thing, memory hierarchies. Now, memory hierarchy is also a response to a basic limitation, that we can build very fast storage or very large storage. So when it comes to the storage, the response to any functions will be there. Okay, so if you need the faster storage or a large storage, okay, so you should think how you have to use the memory in your systems. Yeah, coming to the parallelism alone, first concept here, we actually programs are written as if like instruction were executed in sequence. Now it's the hardware actually where it checks for dependencies in the instruction and try to execute them sequentially or parallelly if possible. Now whenever there is a parallel execution of the instruction, time limit will be, we can utilize the time properly, okay, because time usage will be less over there. Okay, but in some cases, there is a hardware scheduler a component present only in the architecture. So it will support this instruction ordering so that it increases the parallelism and in the program. So hardware scheduler is a component which helps to do that. Next, coming to the instruction level parallelism, it can appear in the instruction set. Okay, we've already seen the instruction set in the two architecture. Okay, SIC and SIC-XC, and now the computer architecture. In computer architecture, if I come across instruction set, okay, there are a lot of instruction sets available, and one among is very long instruction word. Okay, so these machines which support VLIW have instruction that can issue 20 multiple operation in parallel. So you can think of how parallelism works. So the best example which support VLIW is Intel IA64 architecture. Now all high performance of this particular parallelism and also general purpose microprocessors, there are like few other instruction set, okay, so which helps to operate on parallel, so just to increase the performance, right? Okay, next is like parallelism. If we go in detail, you should be able to understand the multi-threaded code also, because we write multi-threaded code for multi-processors or parallel code which can automatically generate by a compiler from sequential programs. So I already mentioned it's the hardware scheduler which decides the ordering of instructions. So depending on that, yeah, looking at the multi-threaded code present for the computer architecture, then it can automatically decide on. So there are like many scientific computing and engineering application where computation intensives can be a benefit, so that it supports parallel processing, and whenever there is a parallel processing by any program or by any applications, yeah, compiler has to support that. Yeah, next concept is memory hierarchies. Hierarchy in the sense it's consists of several levels of storage with different speeds and sizes. So the average memory access time for a program is reduced if most of its accesses are satisfied by faster level of hierarchy. Now, both this parallelism and memory hierarchies try to improve the performance of the machine, but again, it depends on how we use. Okay, maybe it is maybe coming to the compiler as a supportive for this architecture, it can affect the performance of an application as well. Now, these memory hierarchies are found in all the machines. So maybe a processor has a small number of registers consisting of hundreds of bytes, maybe several level of caches containing kilobytes to megabytes, physical memory containing megabytes to gigabytes, and finally it can have secondary storage that contains using gigabytes and beyond. So these are the different hierarchy levels present in all computer machines. So in the sense, like whenever we are using the registers effectively in a single it will be a problem for optimizing. Okay, that we have already seen in the first module when we are using registers directly for our computation. Okay. Now whenever the registers are allowed to manage explicitly in software, caches and physical memories are hidden from the instruction set, which are to be managed by the hardware. So the memory hierarchy is being controlled so that it won't affect the performance of the compiler for any application. Okay. There's a cache management policies, which are again implemented by hardware, which can be effective in a few of the cases, like when there is a data structures like arrays and all will be used. So again, next is it is possible to improve the effectiveness of the memory hierarchy by changing the layout of the data or changing the order of instruction accessing the data. So that is possible. Again, the compiler has to work on. Okay, so that is a second application where you are trying to know the computer architecture. Now, this is the third application where you try to know the design of new computer architecture only. Now here, like in early days, what happened? They just tell you, like in early days of computer architecture design, compilers were developed after the machines were developed. Okay, so but now, as and when the computer architecture is evolving, as in like there are a lot of programming languages coming. So it always a challenge for the compilers, compiler designers who will develop, okay, the compiled code. Uh, it has to take care of the processor design stage, uh, running on the simulators and everything, so that after at the end it has to support both computer architecture as well as also programming language. And there is always a two instruction set. Okay, CISC, that full form is complex instruction set. Okay, that was the previous previously used. Now actually the reduced instruction set computer architecture is being used. Okay, CISC instruction set, it includes a complex memory addressing modes to support data structure accesses and produce innovation instruction that save registers and pass parameters on the stack. Now, Here, I mean, don't, you're just generally talking about the computer architecture, okay? So, there are two different instruction set, which is there, RISC and CISC. You're not going to study in detail about RISC and CISC also, but here, as for the application of compiler, you will just know what actually you mean about RISC and CISC instruction set. That's all. Then compiler optimization can reduce these instructions to a small number of simple operations by just eliminating the redundancies across complex instructions. So it is possible with the compiler optimization if it's using CISC to reduce the instructions, so that it will give you efficient performance. There are other general purpose processor architecture like PowerPC, Spark, MIPS, Alpha, PA, RISC, which are based on RISC concept. x86 architecture is a microprocessor architecture which has CISC instruction set. It's not like CISC was before and now it is RISC we are using. So both are there, and for both this instruction set, whenever the compiler has been developed or designed, it has to think of how exactly it is utilizing this instruction set for itself. And at the end, it's a compiler which has to give the high performance for whichever architecture the computers have been using. Okay, other than that, there are different specialized architecture. They include data flow machines, vector machines, VLI, EW machines, SIMD, full form as single instructions, multiple data, array of processors, systolic arrays, multiprocessor with shared memory, and multiprocessor with distributed memory. They are the different architecture which is available, okay? The development of these architecture concepts has been done from many research, and some of these ideas have been included in embedded machines. Now, as coming to the computer technology, it is always a challenge to support all these specialized architecture, to make that possible, so that it supports all the architecture and finally it gives the end result as an effective one. And one more application is program translation. Okay, so this is a program translation. It is the main application of a compiler. Now, translation from a high-level language to machine-level language. The same technology can be applied to translate between different kinds of languages also. Okay, now we have already used C, Java, right? And Python also. So whichever high-level language, as a user, you are used to, or you like to write the code, okay, but then it is the compiler which translate the higher level language into a machine level language. For the program translation techniques, there are further a few techniques which has to be thought of. That is binary translation, hardware synthesis, database query interpreters, compiled simulations. Okay, so these are the 4 things which is there. Now, binary translations. Compiler technology will be used to translate the binary code for one machine to another, which allows a machine to run programs originally compiled for another instruction set. So I already mentioned it has to take care of both. I mean, whichever instruction set the computers has been using. So this binary translation will help to port, okay, so that it can support any of the instruction set. So it is used in such a way so that there is a availability of software for all the machines. Now, binary translation can also be used to provide backward compatibility. They say that means when the processor has been, I mean, at this moment, at the current trend, if the compiler has been doing its translation, okay, so they have to be I mean it has to be in such a way that it is supportive to the previous version also. That is actually a backward compatibility, so it has to be compatible with every versions of the architecture and all. Next, hardware synthesis. It's like it's it's not like only programming language, the whichever we use, that is high level programming language. It's not like only that part where the compiler um, has to be supportive, okay, so it depends on the hardware design also. So we have just seen in the previous it depends on the computer architecture as well. Now there are like certain hardware, I mean high level hardware languages also. Okay, so they are called as high level hardware descriptive languages like Verilog and VHDL. Okay, so even that so like some hardware functions have been written by these languages, and that has to be also taken care. I mean hardware designs also be taken care for equal participation of the compiler functions. So these hardware languages will be described at the register transfer level. So we call it as RTL level. So it works on the register part. So just try to translate RTL descriptions automatically into gates, which hope you know, which are mapped into transistors and eventually to a physical layout. So that is a completely hardware part wherein that has to be supportive also for program translation. Now once for the main work, that is program translation, this hardware designs will just optimize it more. Yeah, database query interpreters, again, if the applications um, as database in it, so there has to be separate kind of to evaluate that particular language and try to see how the translation has been done properly. And coming to the compiled simulation, I mean simulation in the sense before actual software have been developed. Okay, so simulation has been done to check all the possibilities, okay, so that it is supportive, it is compatible and everything, to check all the features, and finally it is the outcome, the software or the compiler which will be available at the you so that other end users use that. Okay, so all this has to be taken care. And about next is like software productivity tools. This is the last application of your compiler technology. And yeah, programs. No, before actually you start writing the program, you have to think about all the possibilities of what it has to do and all that. So you have to take care, I mean, of the errors which come up also. So some errors may crash a system or it produces wrong results. Okay, or it can be some of the applications may have security attacks, so everything has to be taken care before writing a program. So so testing is like a primary technique which is being done at different levels. Okay, testing is as simple as in locating errors in the program. So there are a few techniques here: type checking, bounds checking, as well as memory management. Yeah. Uh, Type checking, in the sense, it is I've already seen this kind of errors in your programs as well. Whichever data you have been like, yeah, data types, whatever it's there, okay, however the program supports, okay, you're just trying to check whether it is effective usage for that particular program. Okay, so again it depends on our different IO programming language. Okay, wherein program analysis has been done to find the type errors and analyze the data, I mean the flow of data throughout the program. Maybe like if it's C program, if you are using a pointer, you know how pointer has been can be dangerous some of at some point of time. So only at the different higher level languages, pointers have been eliminated. That concept is not there. So that's how the type checking has been done. Next, bound checking. It's always like when now there can be some security breaches in systems where buffer overflow occurs and all such things. Maybe it just failed to use the particular memory at that particular time. Suppose whenever you are using arrays, you know they are static things. They cannot be dynamically allocated depending on the program. So again, depending on the different data structures available, you need to see how the memory has been utilized. So that's about bound checking. You just go through it. I'll give you the slides. Just go through it and try to understand. And finally, it's a memory management. Now, again, you have seen that Java language is actually best because it tries to automatically delete the memory if it's not using it. So again, when memory utilization also matters a lot for any programming language or for the compiler as an application which is built. So there has to be no memory management errors. So that we call it as a memory leaks. And that is actually a main problem for C and C++ programs. So whenever you're writing any, whenever you are using high-level program language for writing any of the application, as a programmer, you won't think how the compiler works and all, but when you're thinking to design a compiler for any program language, that time you should be very careful about thinking what are the different languages available for the applications and how the computer architecture um, is utilized, so it be compiler at the end whenever it has been developed has to be compatible with both hardware as well as programming language. That's all for today. If you have any doubts or if you want to discuss anything on these things, you can just ask me. Any doubts, guys? Maybe we can discuss on this. As you know, many of the programming languages